A train journeys from one station to the next at distance s apart. First, it has a uniform acceleration alpha, and finally decelerates with uniform acceleration beta as it approaches the next station. Find the time it takes to travel between the two stations. First, we need to draw a picture and record the information we are given. Okay. To begin with, we'll have the two stations. Initially, the train will be at the first station at time 0. At the end, the train will arrive at station 2 at time 2. At some point in the middle, the acceleration will change from alpha to beta. Up until this point, the acceleration will be alpha. After this point, we'll have a constant acceleration of beta. The initial location coordinate of the train is 0. And again, there's a location where the acceleration changes. And the location at the end of the train's trip will be S. Now let's write in that here the acceleration is equal to alpha. Here the acceleration is equal to beta. Having written this, we are making the assumption that alpha is positive, greater than 0, and beta is negative, less than 0. So keep that in mind as we use these quantities throughout. Another bit of information that is not given to us explicitly, but we're expected to reason for ourselves, is the velocity. The velocity at time 0, the initial velocity, is equal to 0. That is, the train begins from rest. That is, it was stopped at the first station, and at the end, V2 let's call it, the train comes to a stop at the terminal station. So the velocity will also be 0 there. Now let's look at this from a graphical standpoint, and then we can add in the calculus where necessary. So let's look at a graph. First of all, the information we're given here is acceleration, okay? And we are given not numbers, but values alpha, and that doesn't look like an alpha very much. And down here is beta, which again, as I pointed out, beta is a negative value. So if we graph acceleration, we'll also need to mark on the axes our locations T1 and T2. And the graph is simply constant acceleration. And from there, we go down to the value beta, and again we have constant acceleration out to time 2. Now if we then make a graph of velocity versus time, so we're going to put velocity here, and we'll try to keep the time scale basically the same so that we also have T2 there, T1 here. Then what we're going to find is with a constant acceleration, the velocity increases at a constant rate, forming a straight line. Again, remember, we're beginning at 0 and moving at a straight line. Now afterwards, we'll have a straight line going back down to 0. Notice there is nothing here to indicate that this time T1 is 1/2 of the total time T2, or that the distance traveled from x0 to x1 is half of the total distance. So to keep our answer completely general, we cannot put in that assumption. And I deliberately drew the position up here out of center to remind us of that. Okay. Then once we have the velocity graph, let's sketch what the position graph, because ultimately that is an important part of what they're asking. The other piece of information that they've given us is the position at the end of the trip. Okay, so again, sticking with our time scale the same as before to the extent that I can. T1 here, T2 here. And now we're going to have position, which I will use X for. Again, we've chosen our initial position, our axes, so that our initial position is at 0. And for constant acceleration, we'll have a parabolic type curve. Let me go ahead and mark on the vertical axes. Our end point is going to be S. And we have some other point here in the middle for which we do not know the value. This is our x1. The value up at the top would be x2. So we're going to have a parabola that comes up to this point. And then from that end, you can see that that value is aligned with these. And if we go over to this point out here, we will also have a parabola, but the curvature will be downward for this segment, so that the slope approaches a slope of 0, a horizontal line, as you can see from the graph above. Okay. Now, the key, one of the key difficulties here is that we do not have information about this middle point T1 and x at coordinates x1, or even the velocity at that point. This graph of velocity versus time should help us out with that. And that is, here we recognize that the initial velocity is 0, the final velocity is 0, then the height that the velocity ascends to during the first part of the journey is equal to the height that the velocity descends by in the second half. So let's look at that in terms of our, and we could do it in terms of the calculus. So let's look at that. All right. If we want to look at the velocity, we've got this equation. The velocity, and this will be let's do the velocity at time 2, t2. So the velocity at time t2 is equal to the integral of the acceleration. But since our acceleration is not a continuous function, we will break this integral into two parts. The integral from 0 to t1. And during this part of the leg, part of the trip, our velocity is equal to our acceleration is equal to alpha. Let me erase that. Okay. So our acceleration is alpha. We integrate with respect to time. And then for the remaining part, we have the integral. And perhaps I should put this over on the graph. Notice here, here you see that the velocity is going to be alpha times t. Here, we're going to have alpha t1 plus beta, which is a negative quantity, times t minus t1. All right. So back to the integral. Here, our integral is going to go from t1 up to t2, and our equation is, the value of the acceleration is going to be simply beta, which is a negative quantity, times dt. Okay. so that